Okay, so it's 8, so let's go ahead and get started for today. Our topic for today is going to be, should change the color, open loop op-amp circuits. So I think the first thing that might be of use to you guys is for me to explain what I mean by open loop. So if we look at a functional block diagram for a generic amplifier with an input x of t feeding into a generic amplifier, having some gain A, and then taking our output here to be y of t. This is what we would consider to be an open loop amplifier because there is no feedback loop, which is adding or subtracting something from our input signal. We're going to be dealing with positive feedback amplifiers on Thursday and start talking about negative feedback amplifiers on next Monday. So the absence of a feedback loop is what makes this an open loop amplifier. Then the circuits that we were looking at the end of our last class were inherently open loop circuits, even though we didn't really formalize that. So what I would like to do now is introduce a specific circuit, which we've kind of already talked about. Okay, sorry, that's my doctor's appointment tomorrow. All right, so I'm going to introduce a circuit that we've loosely talked about, but now we're going to formalize things. And that circuit is what's called the comparator. A comparator is simply an op-amp circuit used to compare the strength of input voltage signals against a particular reference voltage. We'll begin by figuring out how a non-inverting comparator works, and then move along to inverting comparators and a couple other brief topics. All right. So a non-inverting comparator circuit looks something like this. We have an op-amp, which requires power. Connected to our non-inverting input terminal, we are going to apply some input voltage. So I'm just going to call this guy Vn as a function of time. Connected to our inverting input terminal, we are going to have some voltage V reference, which is typically a DC voltage. And then we're going to measure our output V out as a function of time here. at our output terminal. So if we drew a practical op-amp model representation of this circuit, it's going to look very similar to what we had at the end of the last class. Okay, so it's going to look something like this. Here is our input resistance Rn. This terminal represents our non-inverting input terminal. This guy is for our inverting input terminal. We have our dependent source here. Here is our output resistance R out. And then this whole bottom thing here is our ground. Our dependent source is providing a gain of our open loop gain, AVOL, multiplied by our differential voltage VD, where, again, just to be clear, VD is always the difference between our non-inverting input and our inverting input. So our output signal is the open circuit voltage seen between the output terminal and ground. So here is where V out of T is. Between the inverting input terminal and ground, we have our voltage Vref. So I'm going to put in a DC voltage source, Vref, like so. And between our non-inverting input terminal and ground, we have our input voltage source. In of T. So how is this different than what we talked about at the end of last class? What is the only fundamental difference here between this circuit diagram and the last diagram that we drew? Right, the reference voltage is not shorted out, okay? So how should we expect this particular circuit to behave? Any thoughts?
Would it be similar to how it ran last time, except for we would just use VD rather than VN?
Yeah, so that's absolutely correct. So the last time we saw that we had a piecewise function, trying to think of the best way to describe this. Let's make a graph. Graphs are always fun. Let's say so I need to give us a few parameters. So our parameters are going to be, so let's see, this is V in, this is V out. Let's say that we're working on a circuit where our open loop gain, AVOL, is 10 to the 6 volts per volt. Our input resistance, Rn, is 5 mega ohms. And our output resistance, R out, is 1 ohm. And our reference voltage, Vref, is equal to 1 volt. Okay. I also, I guess, need to specify power supply voltages because these are going to be important. So let's say that VCC plus is equal to 5 volts and VCC minus is equal to negative 5 volts. So I'm going to put 5 volts here and then negative 5 volts here. All right, so let's say that Vn is negative 5 volts, right, which would be corresponding to way out here. All right, so if Vn is equal to negative 5 volts, what is the expected output of this system? Let's just talk our way through it. We don't really have to do a whole heck of a lot of math, right? So if Vn is negative 5 volts, what's Vref?
1 volt.
Or sorry, I'm sorry, that was my fault. Yeah, Vref is 1 volt all the time. So if Vn is negative 5 volts, what's Vd? That's a better question to ask.
-6.
Negative 6 volts, okay. So that negative 6 volts for Vd is going to be multiplied by our open loop gain of, let's see, 10 to the 6 would be 1,000,000, right? So we would have an output voltage of negative 6 million volts, supposedly, right? Now, is negative 6 million volts more negative than VCC minus? Absolutely, right? So at this particular point, we would see that our output voltage is saturated at VCC minus. Let's take a look at what's going on at an input voltage of 0 volts. Okay, exact same methodology. So if Vn is 0 volts, what's Vd? Negative 1, which is going to get multiplied by a factor of 1,000,000, giving us an output voltage of negative 1,000,000 volts, which is much more negative than VCC minus. So at Vn is equal to 0 volts, we also have an output voltage of negative 5 volts. We okay with that? Does anybody have any problem if I connect these two dots with a line? So I'm suggesting here that if my input voltage is within the range from negative 5 volts to 0 volts, my output is always going to be in negative saturation. I shouldn't expect any abrupt shift, right? Now, when Vn is negative 1 volt, or excuse me, positive 1 volt, what should we see?
It would be 0 volts. Vd would be 0 volts.
So Vd would be 0 volts, which means V out would also be 0 volts, right? So at this particular point, where Vn is equal to 1 volt, we have a value of 0. Now let's look at what's going to happen at 2. So when Vn is equal to 2 volts, what is Vd? Positive 1 volt, which gets multiplied by that open loop gain, giving us positive 1,000,000 volts, which is much larger than VCC plus. So we should see that our output saturates at positive 5 volts. And then let's look at what happens at positive 5 volts for Vn, okay? So at positive 5 volts for Vn, Vd is equal to 4 volts, right? 4 volts multiplied by 1,000,000 is 4,000,000 volts, which is again, much, much larger than VCC plus. So we have saturation. So I'm going to do another thing where I connect these dots because I can pretty firmly say that for all voltages between, or for all input voltages between 2 and 5 volts, bless you, our output should be positive saturation. So really the only thing we're unsure about where this behaves is in the range of the reference voltage, okay? So I can't really draw this on the diagram well, but let's say that our Vn is 1.001 volts. So 1 volt and then another millivolt added to it, okay? What is Vd?
0.001.
Yeah, 1 millivolt, okay? So if VD is 1 millivolt, what is V out?
1 kilovolt.
Okay, so 1 millivolt times a million is 1 kilovolt. I agree with that. 1 kilovolt is much larger than 5 volts. So really, we should see that actually all the way up until just after 1, like on the order of a millivolt or 2, or a microvolt or 2, really, based on this gain, we should see that it's up at positive saturation. What if VD were negative 1 millivolt? We would see the exact same thing, except it would be negatively saturated. So really what we have is something that looks like this. I've drawn this in such a way that the shift looks completely vertical, but it's not. There is technically a slope to it. It's just extraordinarily steep because the linear range of this amplifier is very small, right? Based on our equation for linear range that we developed in the last class, with a gain of 10 to the 6, we would have -5 over 10 to the 6. So the linear range on this guy is literally from -5 microvolts to +5 microvolts. Anything outside of that range causes saturation. So this is going to have an incredibly steep slope in that small transition period. So we can infer a good enough approximation of how this particular device behaves, right? We can say that for our non-inverting amplifier, V out is equal to VCC plus whenever Vin is greater than our reference voltage. And we can see that V out is VCC minus whenever Vin is less than our reference voltage, right? Which is exactly what this graph is showing us for a reference voltage of 1 volt. Now, this is true when AVOL is large, right? The smaller our open loop gain is, the smaller that slope is going to be, and we're not going to get a nearly vertical line. But the overwhelming majority of practical operational amplifiers have voltage gains on the order of 10 to the 5 or more. The smallest smallest open loop voltage gain op amp that I can think of is one that's used in video processing circuits, and it has an open loop gain of about 2,500 volts per volt. So it's still going to have a very, very steep slope. The linear range on that guy is a couple of millivolts plus or minus around 0, right? So on the macro scale, it's still going to exhibit pretty much this behavior. So let's change things slightly. I think there's enough room here. Talk about an inverting comparator. All right, so in an inverting comparator circuit, it's going to be very similar to what we just had. We have an op amp, which, as per usual, requires power. We are going to apply our reference voltage at our non-inverting input, and we're going to apply our input signal to our inverting input terminal, and then take our output here. So I'm not going to bother redrawing everything that we had previously for our practical op-amp model, because it should be fairly obvious what the difference between an inverting and a non-inverting comparator is. I would just change the location of VREF with VN. That's the only difference, right? It's the only difference between the schematic diagram, so that should be the only difference for the practical op-amp model as well. So how do you think this thing is going to behave? If we had all of the exact same parameters as our previous circuit, AVOL is 10 to the 6, RN is 5 mega ohms, Rout 1 ohm, VREF 1 volt, VCC plus 5 volt, VCC minus is negative 5 volts. How do you think this is going to behave?
Would it be
What do you mean by is it going to be? So the fundamental difference between these two circuits is everywhere that we had VDD was a positive number, it's now going to be a negative number, or excuse me, not VDD. Everywhere that VD was a positive number is now going to be negative, and everywhere that VD was a negative number will now be positive because we've switched those two, right? VD by definition is the voltage at our non-inverting input terminal minus the voltage at our inverting input terminal. Since we've switched the voltages that we apply there, we're really just switching the sign on VD from what we saw before. So from that, if I were to plot this, this is VN, this is V out, this is VCC plus, down here will be VCC minus, and here is our VREF of 1 volt. What we should expect to see is something that looks like this, which is exactly opposite what we had before. And it's because we've effectively changed the polarity of our differential signal VD. So does that make sense? Do we need to really go through and analyze this thing point by point like we did the last one? I don't think so. From this graph, we can develop a relationship for the output voltage, just like we did for the last circuit, where we can say that V out is VCC plus, where Vn is less than VREF, and V out is VCC minus, where Vn is greater than VREF. So we really just change the signs on those comparisons, right? Or those less than and greater than operators, okay? So this is a non-inverting comparator and an inverting comparator. Now you may be asking yourself, well, that's all fine and dandy, but what's the use of being able to compare things to a reference value? And so that is going to introduce us to what I hope is a rather trivial design problem. You are asked to create a 1-bit ADC. ADC stands for analog to digital converter circuit. In which input voltages larger than 3 volts generate a digital high output of 5 volts. Input voltages less than 3 volts. Generate a digital low output of 0 volts. How would you create this circuit? Okay, so we can define VCC plus and VCC minus from the problem statement. Okay, so let's put your money where your mouth is and tell me what VCC plus needs to be. I disagree. Should be 5 volts, right? Because our output is going to be VCC plus or VCC minus. So, so we're saying that we're going to need VCC plus is equal to 5 volts because we want our high output to be at positive 5 volts, right? So what is VCC minus? What does it need to be?
0 volts.
0, because that is our low output. What does our reference voltage need to be?
3 volts.
3, because that's what we're comparing our input signal to. And now the $1 million question, am I going to implement this with an inverting comparator or a non-inverting comparator? So with an inverting comparator, when my input signal is greater than my reference voltage, my output goes low. I want, when my input voltage is greater than my reference voltage, for it to go high. So that means I have to be dealing with a non-inverting comparator. So the circuit that would get this done would be Vn goes here. Five volts here, ground here. 3 volts goes here, and here is where I take my output. And we can verify this with LT Spice. So I've made a simple non-inverting comparator circuit. I need to change one voltage because I used a reference voltage of 2 volts for some reason here. Which ones I gotta plug this in? Change to 3, there we go. All right. So let me briefly explain what's going on here. Hopefully everything on the right-hand side, my simple op-amp circuit, makes sense because it's exactly what I just drew. Over here on the left-hand side, I have my power supply voltages set up. For my input voltage source, which is this one labeled V3. By the way, everybody on Zoom can see LT Spice, right?
Yes, sir.
Yes.
Okay, great. So I'm using a sinusoidal voltage. And the reason why I'm using a sinusoidal voltage source is so that I can sweep my voltage from positive 5 volts to negative 5 volts back and forth. It really doesn't matter if I used a square wave or whatever to do this. I just want to be able to vary my input voltage. So I'm just using a sinusoid because I'm lazy. And then my reference voltage is created by just using a simple DC source. So if I run my simulation, I'm going to plot my input voltage, which is again just my simple sinusoidal voltage, and my output voltage. I'm going to play with the limits here just real quick, like So we can see that everywhere that my input voltage, which is the green curve, is above 3 volts, my output voltage is at digital high of 5 volts. And everywhere that my input voltage is less than 3 volts, my output voltage, which is a curve in blue, swings down to, it's going to negative 5 volts because I chose the wrong thing here. So let's put this at 0 and fix it. Sorry for the mistake. There we go. So everywhere that my input signal is less than 3 volts, my output goes to digital low, which is 0. So we have done a design problem in this class. Wasn't particularly difficult, but we have actually designed a circuit which has practical applications. Okay. So let's swing back around here and expand on this a little bit. Having access to a 5 volt supply and ground is fairly common, but having access to a 3 volt voltage source is probably less so. How could we go about setting our reference voltage in a circuit like this without using an extra voltage source? Any thoughts? We can use resistors, okay? So specifically, we're going to use voltage divider circuits, all right? So for this particular problem, I might have something that looks like this. So I'm going to start by redrawing my op-amp portion. I'm going to leave my power supply voltages the same, 5 volts, and ground goes here. I'm not going to change my output signal in any way, and I'm not going to change my input in any way either. I'm still going to apply Vn as a function of time to my non-inverting input terminal. But I'm going to establish my reference voltage by using a simple resistive divider circuit. Where I'm going to have some resistor on top and some resistor on bottom. So what value of resistors should I use? Let's start with maybe an easier question. What is the ratio of the resistors that I should use?
Maybe 2 to 3.
Right. So 2 to 3, okay? Where I'm going to say that the 3 one is here and the 2 one is here. So if I use voltage division, then I'm saying that 3 divided by 3 plus 2, or 60% of my 5 volt VCC signal, which is exactly 3 volts, is going to be my reference voltage. It's actually not going to be exactly that because there is some internal resistance, our input resistance, that we have to take into account as well. So this gets us to where what is the actual size of the resistors we need, right? A 3 to 2 ratio is absolutely what we're looking for, but now we need to be paying attention to the size of our resistors. For this biasing stage, if we made, let's see, what is my input resistance? What was it? 5 mega ohms. So if we made this 3 mega ohms and 2 mega ohms, that would actually be very bad, okay? And the reason it would be very bad is because the input resistance is on the same scale, right? So that means that any current that's flowing here, let's call it I ref for whatever reason, a significant portion of it is going to branch off and flow into that input resistor because it's roughly the same size as what it sees looking down. We can prevent this by simply making, instead of using mega ohm resistors, use kilo ohm resistors, right? So if we have a 2K and a 3K, this current that branches off and flows into the input terminal, the op amp, is going to be very, very small in comparison to our reference current that's flowing through our reference voltage generating resistor network, right? So we have to pay attention to little things like this. Another thing that we would have to pay attention to, right now we're taking our output voltage to be an open circuit voltage, but it's actually very important if we were going to load this guy. So if we were going to measure our output voltage as the voltage drop over a loading resistor RL, which is pretty standard operating procedure, we have to pay attention to the size of that resistor as well. So our output resistance, R out, was 1 ohm. So if we made our load resistance on the same order of magnitude, so we made it just a couple of ohms, what would be happening at our output? Let me draw a little representation here real quick, all right? So we have AVOL times VD over here. Here's ground. Here is our 1 ohm resistor, which is R out. And then here is our load resistor, RL. And let's say that RL is 5 ohms. Well, this is our output voltage, V out, right? When RL, our load resistor, is on the order of the same size as our output resistance, we have a voltage divider circuit where we're effectively losing voltage drop to that output resistor 1 ohm right here, right? So at our output, we're only going to see 5/6 of the output voltage that we would expect. If we instead made this guy a 5 kilo ohm resistor, we're going to see practically all of that expected output voltage, right? So we could additionally use a mega ohm resistor or something like that if we wanted to, but that would kind of be overkill, and it might also have problems if we were wanting to use the current that's being output by the op amp to do anything. Putting a 5 mega ohm resistor in there would lower that output current to a very, very small amount. So typically speaking, you want to bias and load an op amp with kilo ohm size resistors, okay? And we do that because on the input side, a kilo ohm size resistor is smaller than the input resistance. And on the output side, it's larger enough than the output resistance to where they don't really interact. Does that make any sense at all? Okay. So I would keep that in mind when I ask you guys to do design problems and stuff like that. Typically speaking, your biasing circuitry should always be on the order of, or your biasing resistor should always be in the kilo ohm range, because that's really the sweet spot for where op amps behave the way they're supposed to. All right, so that is comparators. That's really pretty much the only open loop application of op amps, is comparing input signals to a specified value. So any questions on this stuff?
Is that a multimeter?
So a multimeter, I'm sure there's an op amp in there somewhere, but I guess it really depends on what function of the multimeter that you're asking about. So like when you're measuring voltages with a multimeter, you're measuring voltages in parallel with your circuit element of interest. Internal to the multimeter, there is typically a very, very large resistance on the order of tens of mega ohms. So if you were trying to measure the voltage drop, the reason why it uses that very, very large resistance is because it's placing that large resistance in parallel with whatever you're measuring and then measuring the voltage. So if the really, really large internal resistance of your voltmeter is in parallel with a small resistance, it really doesn't cause any effect on the voltage that you're measuring at all. But if you're trying to measure the voltage drop over a very, very large resistance, it absolutely will. Similarly, if you're using the ammeter or current meter setting, that is set up to where it has a very, very low resistance, which is placed in parallel, so that effectively everything, or excuse me, which winds up being placed in series with your element of interest, so that everything flows through the current meter. That is why you can't measure, if you hook your current meter up in parallel to a particular resistor or something like that, you wind up burning out your fuse. And it's because all of the current is bypassing your element of interest and flowing through that very, very low resistance of the fuse, which burns it out. So that's why you measure voltages in parallel and measure current in series, because it's how the measurement tool is designed to operate. So with what that has to do with op amps, I'm not sure, to be entirely honest. I don't know what the internal circuitry of a multimeter is. I just know that how it measures things. So, and then for resistance, it's effectively using a test voltage and measuring the current that flows through it, and then the ratio of the voltage of the current gives you the resistor value. Anyway, I have no idea how the diode functionality works on the multimeters. Never looked into it. If you're an EE student, you'll find out in the winter.
Yeah. Can you talk about how we have no margin of error for EEs?
Pardon?
Like EE students have no margin of error this whole year? You can't drop or. It's only offered once a year. All the time. Yeah,
so we can, I mean, this doesn't have anything to do with this class, but we can talk about it a little bit. The short answer is yes. You really only get one shot at most of your classes. The slightly longer answer is I hope to rectify that a little bit next summer. Traditionally, so the classes that you really only have one shot at this year in your junior year would be ELEN 224, which is circuits 3, ELEN 334, which is intro to semiconductor devices. I'm sure it's got a different name than that, but that's really all that it is. ELEN 335, which is analog electronics. ELEN 336, which is analog electronics 2. ELEN 321, which is linear systems and signals. ELEN 322, which is digital signal processing. And then ELEN 313, which is electric fields. And then ELEN 411, which is electric and magnetic fields, but it's overwhelmingly more dealing with magnetic fields. Of those several classes, which are only offered once per year, the ones that the students typically struggle with the most, and this isn't applicable to everybody, some people just hate fields with a passion and won't do well at it, but the one that students struggle with the most is typically analog electronics 1 and 2. So it's 335 and 336.
Spring?
So 335 is in the winter and 336 is in the spring. There are probably more D's and F's given in those two courses than any other course in the EE curriculum by far. Because that is a potential bottleneck that would cause a student to
have a year?
Yeah, completely have to take on an entire extra year's worth of student loans while they're just waiting for that to come back around. There's two things that I am currently investigating the possibility of doing. The first thing would be to remove those classes as a prerequisite for senior design. The reason why I am considering that is because the overwhelming majority of senior design projects don't really use a lot of transistor-based material. That's probably my least favorite option though, because I wouldn't want to prevent a group from approaching a project just because one of their team members doesn't have the necessary expertise there. The second option, which is the one that I'm much more inclined to do, is to offer those two classes in the summer as 6-week sessions. So just a crash course in analog electronics.
6 weeks.
6 weeks for the first one, 6 weeks for the second one, so that the reason why I would want to do it that way is because if you fail 335 in the winter, you obviously can't take 336 in the spring, and you would need both of those classes to get into your senior year. So I would do 2 6-week sessions. One for the first summer session would be 335, 5 days a week, which would be awful, but doable. And then 336, 5 days a week as well. My expectation is that I will hopefully have no more than 3 students enrolling in those classes at any given time. I would highly encourage you to just pass it the first time through.
Seems like way better off.
Yeah. I've had some students and, talking about that kind of stuff. And this is a way that to me makes a lot of sense as motivation to pass those classes. I absolutely understand that they're difficult. But as it's currently set right now, if you don't pass those classes or any class in your junior year, you are putting off your graduation by 1 full year, which means you are giving up, I would say at a minimum, $70,000 worth of salary because you couldn't pass one class. I don't know about you, but $70,000 is enough motivation for me to get my head out of my ass and pass a class. I understand that there are other factors and stuff like that that go into this. It's a very simplified view, but that is definitely one way to look at it. If you can't pass one of these once a year classes, you are literally costing yourself a year's worth of salary and potentially a year's worth of money going into your retirement accounts and stuff like that, right? You're losing a year's worth of the ability to work.
Is that average pay?
70,000 is probably on the lower end of what I've been seeing.
I heard 90, I mean, on the crew of labor, so 90,000. As me.
Yeah, it depends on the area. It depends on your experience and all that kind of stuff. Around here, 70,000 is pretty good. In somewhere like Dallas, 70,000 is pretty crappy. We have undergraduate students regularly leave here with first time ever jobs of 105K plus.
My brother just graduated from UTA in Dallas, and he got a job at Lockheed Martin, and that's apparently Lockheed Martin hires a lot of them.
Absolutely. All defense contractors hire lots of EEs. I got to tour the Nissan plant over in Canton, Mississippi. I think it was the winter before COVID hit, if I'm not mistaken. And they were looking for effectively ICT graduates and EE students more than any other thing. Like mechanical engineers were not even on their radar as with regards to what they need. And this is in the auto industry, which is traditionally where you think most mechanicals want to go to. So our job placement for our program, I've been paying attention to it since I've been the program chair for the last, I've been the program chair for the last 2 years, I think. But I've been teaching senior design and stuff for the last 3. So I've had the opportunity to do the senior exit interviews and all that kind of stuff. And out of the roughly 150 graduates we've had, I know of a single student that didn't have a job lined up when they left. And it was because they were specifically looking for a job in electrical engineering in Bossier City, Louisiana, because they refused to look elsewhere. Still one person. Everyone else had either a job lined up paying, I would say the lowest pay I saw was around 65K. So it ranged from 65K to 105K, or graduate school, where the graduate schools that we're placing students in are University of California at Berkeley, University of Oregon, University of Michigan, Georgia Tech, like really high-end.
From tech?
Yeah, from tech going to graduate schools at really high-end schools. So we do a pretty reasonable job of either getting you a job or getting you in a graduate school that you want to go to.
I mean, if you pass that 1 year or this 1 year.
Yeah, a junior year is brutal. I'm not gonna lie, it was brutal back when I was here as an undergrad.
Is it because we don't have a lot of staff? Is that one?
I think that is definitely part of it, but I would think that it's the junior year of all of the engineering curriculums is the hardest year. And it's just because the freshman year, everybody's kind of doing the same thing. The sophomore year, for most of it, everybody is kind of doing the same thing. The junior year is when you build the foundation of your specific discipline. And then the senior year is you're just tying stuff up and doing senior design. So you're going to learn more new material during your junior year, regardless of what engineering discipline you're in. So if you talk to the MEs, the junior year is the one that kicks their butt. If you talk to the nanosystems, it's the junior year. Across the board, the junior year is terrible for the College of Engineering and Science.
That's when you have no friends.
Yeah. Well, it's either when you have no friends or you have the most, because you guys use stuff like GroupMe and all that kind of stuff to figure things out. But yeah, I refuse to join any of those type things because I believe that you students need a place to bitch about me where I can't hear it. So any other questions regarding, I don't know, our program or class or anything like that? Alrighty, well, we are going to cover positive feedback circuits Thursday. That'll probably be another, let's say, 45-minute or so lecture, and then after that, we'll get into ones that take pretty much the full time.
Are these recorded?
Yes, they are being recorded. I will have all 3 of our class meetings to this point uploaded by 5 p.m. today. They will be uploaded on my YouTube channel, and then I will also place a link to the video on our Moodle page so that you don't have to go through all that crap, because all my classes wind up on the same YouTube channel and I don't do anything whatsoever to organize them there. So it's going to be like circuits 2, circuits 1, 335, 336, 438, 550. It's all, I just dump it there and then put links on Moodle so people can find what they need to find. So. Alrighty, see you guys on Thursday. Oh, sorry, one last thing. I changed the due dates for homeworks slightly. And so what I mean by that is I was thinking about it, and it was rather, I felt it was inappropriate to make homeworks due on Monday and then another homework due on the next day, Tuesday, because this class is a Monday, Tuesday, Thursday structure. So instead, homeworks that are assigned on Monday are due on a Monday. Homeworks that are assigned on Tuesday are due on Wednesday. And homeworks that are assigned on Thursday are due on Friday, so that you always have a gap between when homeworks are due, so that the procrastinators have a little bit more time to do stuff and or a little bit more time to ask questions.